Welcome back, everybody, and thanks for joining once again. Well, we're wrapping up our chapter on forces, and this last segment is going to be on forces that are applied on systems of objects. Now, we've done systems of objects before. We've had problems where you've got one box receiving a force, and that box is pushing on another box, and there's a contact force between them. But this is going to be slightly different because these objects, these connected objects, are connected not by being directly in contact with each other, but they're going to be connected through a string or a rope or something that can apply tension. So it's not really a trick right here, but it's just a way of thinking about this. The way we want to think about systems of objects, first of all, is to solve for the net forces on the entire system. Now this says net force EXT, which stands for external, which is perfectly fine, but I like to write the net force on the system. The net force on the whole system. The system is just a system of connected objects is just sitting there. It's not going to do anything unless some sort of force acts from the outside on that system. The net external force on the system equals what? Well, this looks somewhat familiar to us. Mass times acceleration, but this mass you'll see is a capital M. What does that mean? Well, that means it's the mass of the entire system. So whatever force is applied to objects that are connected together is going to have to be applied to accelerate the whole mass of the system, even if that force is only applied to one part of that system. If that's causing the whole system to move, then the whole system mass has to be accelerated by that force right there. And so our final value, acceleration, is also the acceleration of the system too. That means all parts of the system are accelerating at the same rate. You can't have one accelerating at a greater rate than others. They're all going to accelerate at the same rate, and so we're saying that the whole system has the same acceleration. All parts of the system don't have the same mass, and all parts of the system don't experience the same force. Like individually, they don't, but all parts of the system do have the same acceleration. All right, so capital M is a total mass added up, and net force is the net external force on the system. All right, so let's go ahead and apply this to our first example. Here's what we have. It's an object called a modified Atwood machine. And an Atwood machine is, oftentimes it's two masses, but it has to be at least one mass that is draped over a pulley. And here's our pulley right here. And this mass is draped over it, and therefore the hanging, you might say the weight force of this mass 2 times gravity, is what's going to be causing the system to move. Now the first mass right here is not hanging, it's actually supported by the table. But it is going to be caused to move because of the weight force of this mass 2 pulling downwards. That's why I say it's an Atwood machine. Later on, we're going to be doing some problems on actual Atwood machines where it has two masses hanging and they're both draped over a pulley. But so we have these two masses right here. Now first of all, the problem is that we don't have values for the mass. So I'm just going to go ahead and give you values for mass 1 and mass 2. All right. I'm going to kind of zoom in right here, and we're going to say that mass 1 equals 5.2 kilograms, and mass 2 equals 3.1 kilograms. And mass 2 is the one that's hanging. Okay, it's draped over the pulley right there and hanging straight down. So, I should zoom back out a little bit more. There we go. All right, so this weight force, M2 times gravity, is what's going to be driving the whole system. Now, some good news for us, we've got a frictionless tabletop, so we don't have to worry about friction force that exists in here, at least not for this problem. I mean, it exists in real life, but we're going to assume that it's a frictionless tabletop, like an air hockey table. But we want to find two things. We want to find the acceleration of the masses and the tension in the string. Now, the tension in the string is a force that acts, we talked about tension being a force that acts as a pulling force from end to end. You can't push with tension, but tension pulls. So, tension pulls this mass from this side, and tension kind of pulls up on this mass from this side right here. So tension is kind of a two-way force, as forces act in kind of pairs that act towards the center of the string. But tension doesn't do anything to add to the system. It's not an external force. What external force is causing the system to move? Well, it's this weight force right here, right? If we took this mass and just set it up on the table, there would be no tension in the string, or even if there was tension, it wouldn't be causing the system to move. So we think of tension in this case as being tension as an internal force. Okay, that means it's simply a force that links one object to another, or maybe transfers force from one object to another, but doesn't do anything to accelerate the system itself. Okay, so for part A, we're going to be finding the acceleration of the whole system. Then we're going to be finding the tension in the string. So kind of as a plan of action right here, we're going to be looking at the whole system to find the acceleration. And then we're going to be looking at one of the individual masses, not both of them, but just one of them has a tension force on it to see if we can solve for what that tension is. Okay, so I'm going to take this and I'm going to zoom it out a little bit so I have a little more space right here and kind of move it up into the corner like that. All right, let's find the acceleration of the system. Okay, for the acceleration of the system, of the masses, right? Okay, we can say that the net force on the system equals the mass of the system. Now that's a capital M right there, so that means mass, oops, I'm wiggling that up and down, mass of the system times the acceleration of the system, right? Acceleration of the system. Okay. Sorry I keep zooming in and out like that. So, that's great. We don't know the acceleration of the system, and we want to find that. So that's what we're solving for right there. But we do know the mass of the system because we can simply add those two parts up, right? We can add together 5.2 and 3.1. So we're going to do that in just a minute, but not quite yet. But whenever we solve for equations involving forces, we state the net force two different ways. The net force on the system is, this is Newton's second law right there, absolutely. But the net force on the system is also described as what? Well, what is that force, or those forces that are acting from outside the system to cause it to move? Or in this case, it's the only force on the system. What is the only force on the system causing it to move? It's the weight force right here, caused by this mass hanging down, being pulled down by gravity. Okay, so we can say the net force causing the system to move at all is mass 2 times gravity. Okay, well this should look familiar to us. We've made two statements for net force on the system. Now we're going to set them equal to each other. Okay, mass of the system times acceleration of the system equals mass 2 times gravity. All right, well, we want to find the acceleration of the whole system because the whole system is going to be accelerating at the same rate. What is that? Well, let's solve for our acceleration of the system. Acceleration of the system, to solve for that, that means we're going to be dividing by mass of the system, right? m2g divided by mass of the system, which is really m2g divided by, what's the mass of the system? The sum of those two, right? Mass 1 plus mass 2. Now again, to solve for this acceleration of the system, we're looking at the whole system, well, like I said, as a whole. All right? This is going to be kind of part one. We're going to look at a specific part later on. But let's go ahead and solve for our acceleration of the system. That's going to be equal to, what's mass 2? Mass 2 is 3.1 kilograms times g, that's 9.81. Divide that by the sum of mass 1, that's 5.2 kilograms, plus 3.1 kilograms. Oops, I haven't been writing in units, so I probably shouldn't start. Now, some of you may see the 3.1 kilograms in the numerator and the denominator. We can't cancel those out because it's being multiplied in the numerator, but it's being added in the denominator, so they don't really cancel out. All right, divided by 5.2 plus 3.1, I get 3.6, I would just say 3.7. What? 3.7 acceleration is meters per second squared, right? That's our answer to part A, or just the first part of the question. So that means the whole system, the acceleration of the system, is moving at that rate. It's it's changing its velocity at that rate. This part is moving horizontally, and this part is moving vertically, and that's an example of what pulleys do. Pulleys redirect forces or can redirect vectors, but they don't add anything to it. They just change the direction of them. But every part of that system is moving at 3.7 meters per second squared. Okay, let's go to part B now, the tension in the string. Well, we just got done looking at the whole system right here to solve for the acceleration of the system. But like I said before, tension is an internal force. It's a force that acts between parts of the system. So we're not going to look at the entire system now. We're going to look at one of two parts. All right, and we can look either at mass 2 or at mass 1. Why? Because both of them have tension acting on them. Now, if we want to solve for tension, we can look at just mass 2 or just mass 1 right there. Both of them will work, but if we're solving for tension, we can actually pick whichever mass we think might be easier to use. Now look at it for a second. Which mass has less going on with it? Mass 2 has the weight force pulling down, and mass 1 has the tension pulling upwards on it. Tension in the string. Mass 1 only has the tension force on it. That's the only force that's acting on it. So that might be easier to look at mass 1 because the tension force is the only force on mass 1. It's the net force on mass 1. So let's go ahead and just look at mass 1. You can get just as correct an answer if you use mass 2, but I'm going to use mass 1 because it looks like it may be easier to solve for that tension force right there. All right, mass 1 is sliding on that tabletop right there, okay? And that is 5.2 kilograms. And mass 1 has a tension force pulling out horizontally like that. All right, well, let's make a statement about the net force on mass 1. We'll just put a 1 right there, okay? The net force on mass 1 now, not the whole system, but just on mass 1, is what? Mass of 1, because we're just looking at mass 1, times the acceleration of 1, right? Oh, what's the acceleration of 1? We know what that is. That's the acceleration of the whole system, which is why it's helpful to solve for the acceleration of the whole system first, because that acceleration applies to all parts of the system. Okay? This is Newton's second law. Mass of 1 times acceleration of 1. The other thing that's true about the net force on mass 1 is that it's the sum of all the forces on mass 1. Well, there is only one force, right? We said that's tension. Tension is the only thing that's causing mass 1 to move. If tension went away, mass 1 would not accelerate. So this is the only force. So that's why mass 1 was easy to pick, because there's no other forces to deal with. Here we have two forces acting against each other, but there's only one force on mass 1. Okay, well, let's just sum these up. These are both equal statements. So we can say the tension, which is what we're solving for, equals mass of 1 times the acceleration of the system. We know what mass 1 is, right? That's 5.2 kilograms, and the acceleration of the system we just solved a few minutes ago. That's 3.7 meters per second squared. Those multiplied together are going to get our tension in the string. 3.7 times 5.2, I get 19 newtons. I'm just going to keep it at 2 sig figs like that right there. Okay? It's the same tension that is pulling back up on this mass 2 right here, but we used mass 1 because that was going to be easier. So, for problems like this, we solve for the acceleration looking at the whole system first. Then we solve for internal forces by looking at just one part of the system. Just this guy, or just this guy, because each of those is experiencing that tension force. And even though we only use mass 1, we can be sure that that's going to be the exact same tension force acting on mass 2, because tension is equal acting in all parts of that string. All right, if you have any questions, make sure you let me know. But in the meantime, thanks for following along. I'll see you on the next one.